Welcome to Torah Andalus. We are in class 68 of the Golden Doves on page 33 on the second to last paragraph, mathematics other than geometry. As you know, Torah Andalus, we want to bring Torah and the understanding of Torah to an intelligent level, because there are some people who are not intellectually stimulated and do not have the ability to make a connection with the Torah other than through intelligence, right? And we want to reach out to those people also, meaning Torah and intelligence shouldn't be mutually exclusive, right? That's one of the predicates of this channel. So we want to bring up the Torah to a very intelligent level, and we're hoping to reach out to an audience that is looking for intellectual stimulation through the Torah, right? So that's why we're studying Golden Doves, because it really is a very, very, not just difficult, but very deep book with profound ideas. So I know that this particular section in the book is really tough. So, but if you're listening to this class, hats off to you for sticking with the classes for this long, and you will definitely benefit from this. Mathematics, other than geometry, deals with quantitative relations and functions on the basis, and functions on the basis of successive analysis and synthesis. So before we are dealing with the Greek interest in geometry, because geometry is spatial, and geometry deals with spatial relationships, right? And that's part of the spatial organization and the simultaneous synthesis, which is ubiquitous in Western thinking. But mathematics, other than geometry, so let's say take algebra, take calculus, they deal with relationships that have to do with quantity, right? And in that type of mathematics, what's important is successive synthesis, right? So there's a difference between, you say, x equals 5 minus 3, and if you say x equals 3 minus 5, right? The order matters, right? In mathematics, the order matters. So that's similar to language, where the order of the words in the sentence matter, right? That's a different type of function in the brain, right? That organizes information successively. The structure of mathematics, like that of language, is artificial. Now, of course, this is artificial, right? So the human mind creates language, and the human mind determines here's the proper way to organize the information or to structure the information in the sentence so that you can properly synthesize information. So I say Bill ate a hot dog in the beach, right? That's different than saying the hot dog ate Bill in the beach, or the beach ate Bill in the hot dog, right? So you see the order of words matters. Just like in mathematics, we said x equals 5 minus 3 is not like x equals 3 minus 5, right? And this is artificial. I mean, why should it be like that? But the syntax of language and the way information is structured in language is artificial, right? Similarly, mathematical terms need to be organized into highly hierarchical and stratified structures, as do the components of auditory perception. So in mathematics, sometimes you have 3 plus parentheses, x minus 17 divided by 3. And then, you have that question where do you first do x minus 3, or I forgot what I said, did I say x minus 17? I'm sorry. Do you first do x minus 17, or is it first 17 divided by 3, and then x minus whatever the result of 17 divided by 3, right? So part of the syntax of mathematics is telling you the hierarchical relationships between the terms and what you do before the other thing. And the order, of course, matters. Therefore, to understand the place of successive analysis in these cultures, to understand the place of successive analysis in these cultures, it would be particularly significant to examine the different approaches to geometry and algebra in Babylonia in Greek mathematics. So precisely because these structures are artificial, if we look at these structures, for example, in the Greek culture, and we compare those Greek structures to, let's say, the way the Babylonians structure this information, it would tell us something about their successive analysis of information, precisely because it's artificial, right? All right. However, I'm sorry, and this is a quote. However incomplete, I believe this is from Roman Jacobson, but you can check the text and see, but I think he's about to quote Roman Jacobson here. However incomplete our present knowledge of Babylonian mathematics may be, so much is established by, I was wrong, it's Professor Neubauer, and I'm definitely pronouncing that name wrong, okay? Nevertheless, the name is less important than the sentence. I'm going to read the sentence again. However incomplete our present knowledge of Babylonian mathematics may be, so much is established beyond any doubt. So, of course, there are things we don't know about the mathematics of ancient Babylonia. By this, we're talking about the mathematics in the days of Abraham Avinu, right? But there are some things we do know, and there's some things we know definitely, right? We are dealing with a level of mathematical development which can, in many aspects, be compared with the mathematics, say, of the early Renaissance, right? So it's very interesting how the ancient Babylonians in the days of Abraham Avinu, and I think Philo, if I recall correctly, alludes to the fact that they had a highly developed knowledge of mathematics and astronomy, and Abraham Avinu was privy to this knowledge of mathematics and astronomy, and that's indeed, maybe he's the one who contributed to it, I don't know. But the point is that their level of understanding of mathematics was as great and as developed as that in the Renaissance, which of course was thousands of years later. The principal concern of Babylonian mathematics was algebraic relationships, successive synthesis. Right? Very interesting. That's what they were interested in. They were interested in not geometry, in algebra. And again, there's a difference in algebra in how you structure and organize and order the information. Successive synthesis. Another distinguished historian in mathematics concluded that Babylonians, during 2,000 years before the Christian era, laid the foundations of real algebra. Right. So that's 2,000 years before Christianity. The Babylonians laid the foundations for algebra. In Babylonian mathematics, geometrical concepts, simultaneous synthesis were of secondary interest. So you see how among the Babylonians, geometry was not so interesting. Babylonians never produced a geometrical algebra. There was no concern, as there was in Greek and Hellenistic mathematics, to formulate arithmetical and algebraic knowledge in geometrical language, right? So among the Greeks, they always want to formulate algebra in terms of geometry, shapes, right? So in explaining x squared, you would actually have square, right? And look at the square, and then you would understand x squared. So that's a geometrical approach to algebra, right? Of course, the problem with that is that you become very limited. Then you have x cubed. Okay, so how do you understand x cubed? Well, that's now a three-dimensional square, a cube. But then you have x to the fourth power, x to the fifth power. Well, geez, now that's really tough to visualize. What do you do with that, right? And then you can have, x to the fourth power plus y to the third power equals, whatever number, right? How do you deal with that? So when you think in terms of visual, you're very limited, right? So again, there was no concern for the Babylonians to formulate algebraic knowledge in terms of shapes. Problems that we are used to treating geometrically were solved by the Babylonians algebraically. So because the Babylonians had this algebraic approach where the visual was less, the visual was less important, it was easier to deal with, again, let's say I have x cubed, plus x squared minus 9x, let's just say I have that formula. So now, if you're looking at this again geometrically, it's a very hard formula. if we look at it algebraically, well, how do I deal with that? So I can extract one x, from all these integers, and I'm left with x squared. I don't know what I said, minus x, minus or plus x minus 9, right? So I just took away the x, right? Now I have this, and now I can probably factor this further, right? Theoretically, factor it further. So you can't do that when everything is visual, right? So algebra gives you far greater dexterity than geometry. Problems that we're used to treating geometrically were solved by the Babylonians algebraically. Professor Archibald writes, even where the foundation is apparently geometric, the essence is usually strongly algebraic, right? So sometimes you have a geometric problem, and it really is a geometric problem. But essentially, if you reduce it to algebra, it's far easier to work with the numbers, but for that you need successive synthesis. Illustrated by the fact that frequently operations occur which do not admit of a geometric interpretation, like the addition of areas and lengths, or multiplications of areas, right? How you do x squared times, y cubed. I mean, you can't do that in geometry, right? The predominant problem consists in the determination of unknown quantities subject to given conditions, which of course algebra can deal with quite effectively. Of course, a certain number of geometric relations were well known. So it's not to say that we didn't understand geometric relations, right? We did. But again, treating it or dealing with it spatially becomes incredibly difficult, if not impossible. Numerical calculations are everywhere carried out with the greatest facility and skill. When you have algebra, it's really easy. Oftentimes you have an algebraic problem, which is really easy to deal with, but then when you have to graph that particular formula, it really becomes cumbersome, right? And it may be useful. I'm not saying it's not useful. Sometimes you have a parabola, so you need to see the parabola, and you need to understand, for example, throwing the ball, from a standing position, 0 position, you throw it in the shape of a parabola, and then you come with this sort of algebraic equation, and the algebraic equation reflects the shape of the parabola. And we're not denying that, right? And we're not denying the importance of understanding what a particular equation means, of course. But the point being that if you're going to reduce everything to the visual and use a visual as a way of processing the information and dealing with the information, you'll never make any progress, right? And that's why the algebra of the Babylonians was so powerful, because it really enabled them to reach high levels of understanding or high levels of processing information, right? That was the end of the quote of Professor Archibald. Back to the text. Greek mathematics is essentially geometrical, as noted. Numbers appear to represent magnitude rather than quantitative relations, right? There was a notable concern, right? So in correct mathematical thinking, you're always looking at relationships between numbers, right? So numbers have relationships to each other. What is a relationship, right? So the relationship is expressed in the following formula. For example, the Greeks were interested in magnitude, the size, the shapes. There was a notable concern to formulate even simple arithmetic and algebraic knowledge in geometrical language. I remember when I used to be young, I used to read books on mathematics, and they would always do that. There was a book called Mathematics for the Million, and they would always take what were simple algebraic expressions, and they would turn it into geometry. And it used to confuse me a lot, what? Why do it that way? And I guess they were trying to follow the Greek approach, thinking that if you build upon the Greek approach, it would create certain understanding, and perhaps it did. I'm not denying that, but it was so cumbersome, and it was almost like trying to twist your arm around your body to get to the same size again, right? Side again, right? This concern resulted in the development of geometrical algebra. Since geometry is nothing more than the application of mathematics to the measurement of 2 and 3-dimensional figures, the inclusion of geometry in mathematics would make as much sense to a Babylonian mathematician, or to many modern ones, as would the inclusion of accounting and astronomy in that same discipline. So you can twist mathematics and use mathematics for the purpose of accounting, right? And then, teach mathematics in terms of accounting, but then you're never teaching the student real mathematics, right? But so you can do that, but that's what the Greeks did. They twisted the mathematics, or rather they processed the mathematics only through geometry, which gives you a very limited ability to use mathematics in its pure form and then apply it to other disciplines. In the following remarks, Neugebauer, again, I'm definitely mispronouncing that name, I apologize, addressed himself to this issue, and here's a quote. Compared with the algebraic and numerical component in Babylonian mathematics, the role of geometry is rather insignificant. Right, again, in Babylonian mathematics, which was concerned and focused on algebra and the relationships between numbers, we don't care about geometry so much. I mean, it's just one application of mathematics, but it's not the only application of mathematics. This is, in itself, not at all surprising. The central problem in the early development of mathematics lies in the numerical determination of the solution, which satisfies certain conditions, right? So in pure algebra, we just want to understand, what are the solutions to x, right? If I say, I'm throwing out a number then, and maybe there is no solution to this, but I'm just, doing it for if I say x squared, minus 15x, plus 3 equals 0. So what are the solutions to x? X can have maybe more than one solution, right? So what are those solutions? That's what we're interested in. And then we can apply that to different disciplines. At this level, there is no essential difference between the division of a sum of money according to certain rules and the division of a field given size into, say, parts of equal area. So now I can use that formula to explain how to divide money. Or I can use a formula, the same formula, to explain how to divide a field into two, right? It's the formula that matters, right? And in algebra you have that a lot. So you'll say, Sally bought 10 slices of pizza and 7 drinks for $10, and Julie bought 5 slices of pizza and 3 drinks for $5. How much do the slices of pizza and how much do the drinks cost? It's a simple algebra. It really is. You just create 2 formulas, but whatever. But I can use the same thing, not for pizza and drinks. I can use it for measuring other quantities, and other relationships, right? But once you have the formula in its pure form, you can apply it to different situations. Right. In all cases, exterior conditions have to be observed. In one case, the conditions of the inheritance. In another case, the rules for the determination of an area or relations between measures or the customs concerning wages. So, for example, I can also say the same idea. We spoke about Sally and Julie. You can say Sally threw a ball, 10 feet in a certain number of seconds, and Julie threw the ball, 8 feet in a certain number of seconds. And again, I can create an algebraic formula to say something about the time, the distance, and the speed of the ball. The mathematical importance of a problem lies in its arithmetical solution, right? So geometry is only one among many subjects of practical life to which the arithmetical procedures may be applied, right? But so again, the idea of focusing solely or almost solely on geometry and using geometry as a matrix through which to understand algebra is not just artificial, but it puts the cart before the donkey, right? And then it limits your thinking to geometrical thinking, and then you have an inability to apply algebra to other situations or to other disciplines. End of quote. Now back to my father's text. The inclusion of geometry in mathematics and the formulation of mathematical knowledge in geometrical language and concepts among the Greeks indicates a preference for visual thinking. So remember we said that because these systems are artificial, it tells us something about their mind. So the fact that the Greeks did this means that they were overly focus on the visual. And simultaneous synthesis and analysis, right? That's what the Greeks thought about, which is part of Western thinking, which is part of metaphysical. Indeed, the fact that it is nearly impossible to conceive of modern mathematics without geometry is further evidence of the place of visual thinking in Western culture. Right, right. They could only the Greeks were only able to think of mathematics in terms of geometry. By the way, and this is common in America. I mean, you know, the whole basis of American culture today has become again. I mean, it verges on actual insanity. So, you know, there's police brutality in America. There is, you know, not every situation is police brutality, but there are some situations where there is police brutality. Apparently, there was something that just happened in Memphis, Tennessee. I saw a video. It certainly appears to be police brutality, and not all situations are. I'm not one of those, you know, people who say, oh, everything is, you know, anytime the police uses force, it's brutality. But apparently, in this case, the person who they were beating was submissive, and there was no reason for that. So I would designate that as police brutality. I would not designate police brutality if somebody's resisting arrest and, you know, and you're not cooperating with the police and they use force as long as it's not excessive. You know, but anyway, putting that on the side, my point is not to discuss what is and what isn't police brutality, but it happens sometimes. So there was a situation in America where and I'm mentioning the color, it's irrelevant to me, but it's very important to the society. So it was four black police officers, they literally beat to death a poor black individual. You know, feel bad for him. It was a terrible video to watch. And I'm happy to say there was very little rioting, and there shouldn't be rioting. But if it was four white police officers beating the black victim, again, unjustifiable. We don't support police brutality, but there would be rioting. There would be you know, crazy, you know, fires, and so we see that fundamentally American thinking is predicated upon the Greek visual, or rather the focus on the visual. If it's a black and a white, or if it was black police officers beating up a white person to death, nobody would even, it probably won't even make the news. That would be just irrelevant. So what I'm saying is that you see that in American thinking, the visual trumps everything else, right? They're obsessed with the visual. They're obsessed with how the skin color is, right? And in fact, now many of the large companies in America, they have racial quotas, not just racial quotas, but they actually discriminate against people whose skin color happens to be white, which is remarkable. I mean, it just shows such a low level of intellect. I'm amazed at how American society has devolved in such a dramatic way, where the skin color of the person you're hiring somehow matters, to the extent where you would say, well, this person is a white, we don't want him. This person is black, okay, we'll take him. It's an insult to black people, by the way, because you're telling black people we're hiring you because of your skin color rather than because of your skills. And there's many skilled black people, just like there's many skilled white people, right? So you see that the Greek thinking has its clutches on Western society, right? Continuing in the text. Right. This basic point was noted by Professor Wilder concerning the controversy between Gienz, Veblen, and Whitehead about whether to include geometry and mathematics. In fact, including geometry and mathematics was so artificial that there was a machloikis controversy among some of the professors whether it should even be included as a discipline in mathematics, right? Why should it be? There's arithmetic, definitely mathematics. There's algebra, definitely mathematics. There's calculus, definitely mathematics. But there was a question, why are we including geometry as a mathematical discipline? And here's a quote of Professor Wilder, and again, probably mispronouncing, maybe it's Professor Wilder, that some people think visually and others not, has been widely observed. Right, yes, some people think visually. And granting the distinction, perhaps the case is that Jens was one who did not think visually, so that geometric patterns were of little value to him. So apparently, Jens was on the side that said, why are we including geometry in the study of mathematics? That makes no sense. Whereas Veblen and Whitehead, both of whom most made notable contributions to geometry and its derivatives such as topology, are to be numbered among those who thought visually, right? So machlokes between this side and that side. So Veblen and Whitehead said, no, we should include mathematics, and there is geometry in mathematics because they were very interested in topology, which is the science of shapes and figures, right? The author has long had a feeling that he could easily classify the algebraists with whom he had been intimately associated into two groups: visual thinkers and non-visual thinkers. Isn't that interesting? Right? So you have people know algebra, some are visual thinkers, some are non-visual thinkers. Very important. Right? You can't understand Torah and Mitzvah unless you understand the human mind. And you can't understand the content of the Torah unless you understand the difference between visual and non-visual thinking. As the pasuk says, "Ki lo re'item kol temuna," right? But then the pasuk says, "B'chol ha'am ro'im et hakolot." So what does that mean? You can't understand any of this unless you understand the difference between visual and non-visual thinking. Partly because being a visual thinker himself, he seemed to understand the former much more easily, right? And that's why, according to him, he would have to include geometry. And probably because the manner in which they present their concepts reveal an underlying geometric pattern. So that's the end of the quote. So you see that it's a mahloket among mathematicians. Do we include geometry? Don't we include geometry? Thought and experience may also be organized in terms of. I think this is a good place to conclude our lessons for today.